Oh, it started right away. Okay. Friction. What is friction? Friction is due to the interlocking of molecular hills and valleys between a surface and an object on the surface. When two objects slide past each other, Joe, if you zoom in, even though they feel smooth, on the atomic scale, they're much more like that. This is one theory of friction. There's still, as far as I know, some debate as to exactly what's going on, because to zoom in that small atom is just really tough. You're trying to zoom in on molecules. It's much tougher to predict what's going on. But what we can say is this: friction resists sliding. In fact, to me, Caden, that's kind of the key concept. Whichever way an object is trying to slide, friction will point in the opposite direction. That's how we'll figure out the direction. Because of that, it can resist motion, like when you're trying to slide something. It can also create motion, such as for walking or rolling or cars. Example 1 says, draw the direction of friction in each case. These notes were typed up by a friend of mine in Word 95 for Mac. We're now in 2023. The 1995 Word is a bit glitchy. It may look, when you zoom in, like this block is floating. It's not supposed to be floating. That's supposed to be sitting on the surface. So don't think, oh, it's like on a cushion of air, like an air hockey table. It's not. Just a typo glitch. But Jacob, what direction is the block trying to slide? Which way will friction be pointing then? Yep. What about for a car? When you step on the accelerator in a car, what actually happens is you make the tires try and push backwards against the road. They try and slide backwards against the road. Friction resists sliding. So, Carter, what direction is friction pointing when you step on the accelerator? Yeah, this is a really, really tough concept for students and non-students to wrap their brains around. Years ago, I was at a physics conference, and there was a teacher who had drawn her free body diagram for a car as gravity. I had no problem with that. Normal force, I had no problem with that. And then they had drawn engine friction. And I said to them, that's wrong. I said they didn't know why it was wrong. I said, well, if you put it on ice, you have no friction, but you should still be able to drive. You've all seen what happens when you step on the gas on ice. The wheels do what? They just spin in place. Why? No friction. So, Aaron, a car engine is not what makes a car go forwards. In our free body diagram, what makes a car go forwards is friction. No friction, no drive. People don't realize that. I've probably just explained half of the accidents in the winter. You need to you know what the other half is, Aaron? When you step on the brakes, the car brakes try and push forwards against the pavement. They try and slide forwards. Aaron, friction resists sliding. Which way will friction point when you step on the brakes? When you step on the gas, friction will. What? What? You're right. In other words, if I go back to my car free body diagram, Aaron, when you step on the brakes, this is the free body diagram. So, ready, Aaron? If you're driving on ice where there's no friction, can you stop? I'm a good driver. It has nothing to do with how good a driver you are. I showed you the video a couple of classes ago of the cars sliding on ice. It looked like they were in deep outer space because they kept going in a straight line at a steady speed. Friction is what makes a car go forwards. Friction is what makes a car come to a stop. Not F engine, not F tires, not F brakes. Friction. What does friction depend on? The amount of friction depends on two things. Aaron, I'm talking to you because you're one of the newer humans. You may have noticed some surfaces are slippery relative to each other. Some surfaces are sticky relative to each other. We have a name for that. We call it the coefficient of friction. The coefficient of friction is a ratio that describes how sticky or slippery two surfaces are relative to each other. So here is the coefficient of friction, and the symbol for that, Aaron, Greek letter mu, this thing right here. Okay? So the coefficient of friction, the mu looks like that. It's a ratio. The closer it is to 1, the grippier two surfaces will be relative to each other. The closer it is to 0, the slipperier two surfaces will be relative to each other. So if mu is large, lots of friction. Mu is small, little friction. Those of you who had physics last year, what are the units for mu? Yeah, it's dimensionless, has no units. Just to give you an idea, Aaron, steel on ice, 0.01. That's why ice skates work so well. You push, you'll glide for quite a while. In fact, what's slowing you down the most is air resistance, not friction. Rubber on concrete, it's about 0.75. That one varies a lot, though. You've all noticed on a hot summer day, is pavement slipperier or stickier? Yeah, except it actually changes over time. If we have a long drought, like 30 days without rain, so much oil and chemicals and smoke starts to cover the pavement that you might notice, oh, it's actually pretty slippery. Those of you that are getting your driver's licenses, you should know anytime we have the first day of rain after a long extended drought period, be aware a lot of that water has oil mixed in with it because there's so much that was just on the roads waiting to get washed off. Slow down. Friction is even less than you're used to with just a regular rainy day in the winter. So just be cautious. What else does friction depend on? Again, Aaron, we're going to go Captain Obvious. If you're sliding something across a floor, what's more difficult to move, a heavier object or a lighter object? Be obvious. So at first we thought maybe friction should depend on mg, but then we took it one step further. And we said, we've noticed if you are sliding something heavy, if you lift up, easier to slide. If you push down, way tougher to slide. And so we thought about it last year. And we said, yes, it is true that a heavier object is tougher to slide, but instead of mg, what was a better force to use or indication to use? What was friction equal to? Mu times the? We went with the normal force. We said it really depends on how hard the ground has to push up. And so for a heavier object, the ground has to push up harder. But if you lift up, the ground doesn't have to push up as hard. Or if you push down, the ground has to push down harder. Okay? So, what also friction depends on is the normal force. In fact, if you want to, in this box at the bottom of the page, Joe, here it is. It's on your formula sheet, but most of you will memorize it. Friction is mu times the normal force. By the way, there is no formula for mu on your formula sheet. Well, it sort of is. Get the mu by itself. Yep. Notice it's newtons divided by newtons. The newtons would cancel alpha. That's why mu is dimensionless. But if you ever ask to find the coefficient of friction, that's what you'll end up doing. Let's go back up here. Let's look at this little thought puzzle. Example 2. Consider the block below. You know what? Let's cross out the word block. Let's make it a bench. In fact, let's make it those wooden benches at the back of the gym that you sometimes slide around. Okay? Let's say that Anderson is pushing the bench along, and he's pushing it along at a constant speed. That's going to be important. Suddenly, student number 2 pushes down on the block with a force. Gibson comes along and decides he's going to sit on the bench while Anderson is trying to push it. You've probably seen that happen once or twice before. If Anderson doesn't change his pushing force from before, what happens to A, the weight, B, the normal force, C, friction, and D, the motion of the block? Well, to get a handle on what's really going on, Anderson, this is a job for a free body diagram. I kind of did one for when you're pushing before Meathead Gibson comes along and wrecks everything. Yeah. Wow, Gibson, you didn't see. He just started nodding his head enthusiastically there. There was a lot of agreement with that statement, so I don't know what's going on there. Okay, Anderson, let's do the free body diagram for the bench after Gibson sits on it. What are the forces acting on it? We'll get the obvious one. Yeah. Is it sinking into the ground like quicksand? Is it flying you like Superman? So there's going to be a normal force. In this case, is the normal force going to be bigger, smaller, or the same size as gravity? Why? Because now it's not only having to cancel out the mg of the bench, it's having to cancel out the mg of a meathead, right? I'll exaggerate it so it's stupid obvious. Okay. What's going to happen to friction? Bigger, smaller, or the same as the first free body diagram? And convince me. What? Why? Friction is what times what? What just got bigger? So what just got bigger? Friction. Yeah, yeah. So now we can answer the questions. First of all, what happens to the weight of the bench? When I say weight, what's that a synonym for? Yep. Nope. Your normal force is called your apparent weight. It's not your actual weight. It's how heavy you feel. It's how heavy you apparently feel. So it's often nicknamed the apparent weight. The astronauts on the ISS have an apparent weight of 0. No normal force. What's weight a synonym for? Yes. So Gibson, did the mass of the bench change? Did gravity change? So weight, no change. Gibson, what happens to the normal force when you sit on it? Normal force increases. My abbrev for increases is an arrow pointing up. Alfie, what would be a good abbrev to use for decreases? An arrow pointing left. Oh, down. That's way better. Yeah, let's use yours. Down. I like that. Mr. Dueck, you told that joke last year. Yeah, but he didn't hear it. It's funny to him. Oh, Alfie, what happens to friction? Bigger, smaller, or stayed the same as the first free body diagram? Why? I can tell you're thinking it right. We got this. Yes. And why did that get bigger? Are we sinking into the ground like quicksand? No. Are we flying through like Superman? No. That means vertically the forces must be. I'm looking for that starts with the letter B. And what that really means is everything down has to equal everything. And because there's more down, there has to be more up. Right? So friction increased. So Anderson, back to you. What's going to happen to the motion of the bench? You were initially going at a constant speed. Gibson comes along and sits on it. How is the bench going to behave? Yeah, slows, and then, in fact, in this case, it'll come to yeah. The only workaround is, and if you've ever tried this when your friend is sat on it, what? You've got to increase your pushing force. And now it's got to overcome the new force of friction, usually quite a bit tougher. Oh, in fact, it may be so tough. When you're pushing, what's pushing you forwards? Between your sneakers and the ground is what's pushing you. Friction between that is pushing you forward. It may be Gibson might be so heavy that when you try pushing him forwards, your feet slide backwards because, sorry, not enough friction between you and the ground. It says explain your answer using principles of physics. Our free body diagram in this, I would say, is sufficient. Next page. Ooh, another nice thought puzzle. A student gives an old shopping cart a big push on a flat, rough surface. Which of the following is the best free body diagram for the cart after the student has released it. So let's pretend the cart is moving to the right. And what we're talking about, I don't have a cart, I got a little office chair here. Sorry for those of you on YouTube, but the student gives it a push. We're talking about after it's left the student's hand, right there, but not there, not after it's come to a stop. Which of those four diagrams do you think is the best free body diagram? You know what? We get to vote. Once again, on how you hold your hand up is how sure you are of your answer. So look at A, B, C, and D. Who says, it's A? I got 1, I got 2, I got 3, I got 4, I got 5, I got 6, I got ooh. We have the dreaded lots. Take away 1. Who says B? We have the 1. Who says C? No one's going to vote twice. D. Had you guys voted before? You're changing? Both of you? Boy. You know what I would do? I would probably answer this with a process of elimination. Why must D be wrong? So Carter, look at the free body diagram. What direction is there an unbalanced force? To the? Which way would it have to accelerate? To the? So that would speed up. This would be the good free body diagram for while I was pushing it, maybe? Although there should still be some friction. Why must C be right? Well, in C, the forces are, Alfie, I'm looking for a word that starts with the letter B, which means the net force is 0. How will that behave? It won't accelerate. So if it was stopped, it'll stay stopped. If it was already moving, keep going at a steady speed. So that can't be right because that wasn't what was happening with the cart. I'm sorry. Why is B wrong? Vertically, it looks like the forces are in balance. Horizontally, either friction here is a tiny bit shorter and it would be accelerating to the right, or if they're meant to be the same size, it wouldn't be accelerating at all. Which is the only one that clearly has an object slowing down, or as we think of it, accelerating to the left? Gotta be. Yeah. Adam, no pressure. Which one of Newton's laws did I use to answer that? Now, I told you last year and this year as well, I won't ask you to memorize which one is Newton's first and which one is Newton's second and which one is Newton's third. I will never ask you which of the following is Newton's third law. I won't. But you can memorize them and use them in your answers. If not, you've got to write a longer answer. So which of Newton's laws did I use there? The one that helped me explain whether an unbalanced force will accelerate something or not. Okay. So if Adam had known, he could have written just as his answer Newton's first, and I would have lived with that. Since he didn't know that, we'll have to write only A has an unbalanced force slowing down. But you could have written. Now, the risk with that is if you memorize them wrong, if you wrote, I think that's Newton's second. I don't think it is. What is Newton's second? F equals ma. What's Newton's third? For every action, there is an equal and opposite reaction. Or, as Mr. Dueck says it, forces come in pairs. Okay. But again, I told you you didn't need to memorize which one is which. You should know the 3 laws are there. Example 5. Ooh, getting hoarse. We're going to just finish with this question, and then we're going to hit pause, and we're going to go over your test. For each of the blocks below, write a vertical force equation. You know what? I think the first thing I would do, Joe, is I would actually divide my page in 2, kind of like that. Joe, A says write a vertical force equation. Before I even do that, you know what this is a good job for? free body diagram. What are the forces acting on this 10 kilogram mass? Get the obvious one. So let's put that in. Is the 10 kilogram mass sinking into the ground like quicksand? Flying into like Superman? So there has to be a normal force up, and I think it's the same size as mg. What else? This 20. See it on the picture? What do we call the mystery force coming from off the page? Yeah, I'll put an arrow here, and I'll just say 20 equals F applied. Is there friction in this question? Yes. How do I know? They stuck in the diagram somewhere a coefficient of friction. Not a big coefficient of friction. If you were walking on that, that's not as slippery as ice. Be about like walking on slippery mud, where you still kind of got to pay attention and watch, but as long as you're careful, you're okay. So which way am I going to point friction, Joe? And I'm going to gamble that it's smaller than F applied. Second right-hand diagram. What are the forces acting on it? Get the obvious one. Hasn't changed from before. What else? Normal force. Here's the question. Are we bigger, smaller, or the same size as mg? First of all, how do I know we're not the same size? Extra vertical force in the question. So by pushing down with an extra 15 newtons, is the ground going to have to push up harder to cancel all of that out, or is it going to be able to ease up? So bigger, bigger. I'll exaggerate it so it's stupid obvious. We still have our 20 newtons equals F applied. We still have friction. I'm not sure if it's bigger or smaller. I'll assume it's still smaller than F applied, but maybe I'll be wrong. Okay. Well done. Let's, Joe, let's do part A together as well. So A says write a vertical force equation. In both situations, are we sinking into the ground like quicksand? Are we flying here like Superman? So that means vertically the forces must be, I'm looking for where it starts letter B, which really means what goes, all the forces up have to equal all the forces. That's an equation. In the first diagram, what are the forces pointing upwards? What are the forces pointing downwards? Normal force equals mg. In the second diagram, what are the forces pointing upwards? What are the forces pointing downwards? I heard gravity and data the type of so normal force, everything up has to equal, what is everything down? Gravity and what else? Don't overcomplicate it. Read me the 2 digits. Yeah. That's my equation for the normal force in that situation. Yep. Ella B says find the force of friction. How would I find the force of friction? Friction is what times what? Oh, let's write that down. Friction equals mu times the normal force. Do I know mu? Hey, what's mu? I don't know. What's mu with you? What's mu? I don't know the normal force. Oh, but look. I know another equation that's I can substitute in for the normal force. Which one? mg. So if I crunch this, I'll get 0.12 times 10 times 9.8. Oh, I can do that in my head. Times 10. 10 times 9.8 is going to be 9.8. 9.8 times 0.12, it's going to be, oh, sorry, 98. It's going to be 0.98 plus 1.96. It's going to be 10.8 plus 0.96 is going to be 11.76, I think. Yep. 11.8 if you wrote it that way. Ooh, let's keep going, Ella, to the right-hand side. What did you say friction was? What times what? I don't know the normal force. Oh, but look. I know another equation that I can stick in for the normal force. It's going to be mu bracket mg plus 15. Ella, what's mu? I don't know. What's mu with you? 0.12, yes? And then it's going to be 10 times 9.8 plus 15. Do that one on your head, Mr. Oh, maybe I can. 10 times 9.8 is going to be 98 plus 15 is going to be 108. It's going to be 113 times 0.12. So it's going to be 11.3 plus 2.26. 11.3, 13.3 plus 0.26, 13.56, I think. And that's going to be newtons. 13.6 if I reported it to 3 sig figs. C. C. Okay. Jacob, what does C want me to do? Oh, that's our winner minus loser. Who's winning? Losing equals. What about for C? Really? Oh, that's cool. Aaron, what does D want me to find? How would I get the A by itself? Yep. A is going to be F applied minus friction divided by M. In fact, I can solve this now. Aaron, F applied was 20, right? Minus 11.76 divided by, well, if I'm dividing by 10, I should be able to do this in my head. Sure, I can. 20 take away 11 is 9 to 0.76 is 8.24. 0.824, I think. Meters per second squared. And over here on the right, it's also going to be A equals F applied minus friction all over M. Same equation, because as Jacob pointed out, the original is the same equation. In fact, it's going to be A equals 20 minus 13.56 divided by 10. You might be able to just backspace and edit on your calculator and change the acceleration from the one version to the other. The friction from the one version to the other. I can do this in my head. 20 take away 13 is 7. Take away 0.5 is 6.5. 6.44. 0.644, I think. That's going to be meters per second squared. I'm going to pause here.